Okay, YouTube, in this video we're going to introduce combinations of functions. That is, if we had two functions, say f and g, that have some sort of overlapping domains, that is, their domains aren't mutually exclusive from one another, what we can actually start to do is, say, add two functions together, or subtract them, or multiply or divide them. We call these combinations of functions for very obvious reasons. So before we start doing an example here, all I want to do is make a point to point out the notation here. But basically, if I were to take two functions f and g, and I say, let's go find f of x plus g of x. That is how I would, probably write this in, say, an algebra course. Well, with, like pre-calculus, you're going to see this notation a lot. We say the new function f of x plus g of x it's got a name. We call it f plus g of x. So f plus g of x is really just the sum of the two functions. We would write the difference as f minus g of x, and that would be the same thing as just taking f of x minus g of x. Fg of x would just be the product of these two functions, and then f over g of x, that would be f of x over g of x, given that we can't allow x or g of x to be 0 here because we don't want to get an undefined function. But basically, what I'd like to do is, given these two functions here, and I notice that I have some linear first degree functions, what I want to do is find the combinations of these, their sum, difference, product, and quotient, and also write their domains. So let's go ahead and start with what would f plus g of x look like. Okay, so keeping in mind, we write that now this way, f plus g of x, it's the same thing as f of x plus g of x. So when we say, well, I'm acknowledging that it's just the sum of these two functions, what I'm really wanting us to do is this. We would say that we're just going to perform a substitution, where this is going to be our f of x function, this is going to be our g of x function, and then the sum of these two is just going to be f of x plus g of x. So we say f of x is 2x minus 5. We get 2 minus x here for our g of x. And then to find the sum of these, it's really actually kind of a simple thing. We just add them together. So combining like terms, I get 2x and negative x gives me just an x. We say negative 5 and a positive 2 is a negative 3. So this function right here, this is our f plus g of x, this new function that is their combination, okay? I'll do the domains when I roll back through these. Let's go ahead and find the rest of these combinations here. So we say, what about their difference? Now, it is important to point out here that this is f of x minus g of x. Would we get the same thing as if we took g of x minus f of x? And, simple responses, you just don't. You don't always. You might, but you don't, okay? So in this case, we get f of x minus g of x. We're really just going to do another substitution here, where we're putting in our f of x function. F of x is just 2x minus 5 minus the g of x function, 2 minus x. And I do want to make it a point to go ahead and distribute that negative throughout here. But again, combining like terms, what we end up with in this case is 3x. We get a negative 5 and a negative 2 gives us a negative 7. So this is our f minus g of x. So let's confront our product function. We have fg of x, and I'm not actually going to write f of x times g of x this time, even though that is exactly what we're getting here. But we say f times g, we have 2x minus 5 times 2 minus x. In this case, we actually are going to have to FOIL this out. So we get 2x times 2 is 4x. We get 2x times a negative x here. Whoops. Times a negative x, we're going to get negative, and we get 2x squared. Here we get a negative 10x. And then finally we get a positive 5x. So we do need to combine like terms, simplify wherever possible. And I am going to write that 2x squared in front so that this is written in standard form. Remember that, actually, we need to take a look at this here. 2x squared, okay. This is not a 5 here. Or not a, oh, pardon me. This is not a 10x. When I took negative 5 times 2, I actually get a negative 10. My bad. But combining like terms, let's try this again here. Essentially 2x squared, and it was negative. We got 4x and 5x is 9x. And then we have minus 10. Sorry, I thought I had missed something there, but this is our standard form of that combinations of functions. And then we say, okay, the last one here is f over g of x, okay? And this one's my favorite. The reason why is because when we do this substitution, all we really need to do is just write them in. That is, I get f of x is 2x minus 5, g of x is 2 minus x. And that's it. I mean, that's all she wrote. This is our combination of functions in this instance. So the last thing I did want to mention is their domains. Now, given the fact that both of these are linear functions, then their domain should be an interval notation, negative infinity to infinity in both of these, okay? So when we talk about their combinations, I do want to make a note here, but their combinations, let's write a little text bubble here. The combination of two functions has a domain that is equal to all domain values that were shared by the original functions. Okay. There is one more stipulation here. We say also exclude values for which a quotient denominator equals 0. So we'll look at both of these instances here, but basically what I'm saying is this. Since these are both linear functions, if I were to write the domain of this first function, we say the domain of the first function, domain would have been negative infinity to infinity. It's easy to just go graph this and see it's a line, so it's defined for all values. We say the domain of this function, though, is negative infinity to infinity. So what I'm saying over here is the combination of these two functions, such as f plus g of x, its domain is going to be equal to the domains overlapping here. And I say, well, where do these two domains overlap? Well, they overlap all over each other here, from negative infinity to infinity. And the same is true for this right here. We say the domain of this function is negative infinity to infinity. We say the domain of their product. Domain of their product would be negative infinity to infinity. It's just this very last one here, and this is where this second stipulation applies. We exclude values for which a quotient's possessive denominator equals 0. So I would say that since I have input values down here in this denominator, we need to be careful. We're going to set the denom equal to 0 and solve for x. So denom equal to 0, solve for x. Those are values for which we'll have to exclude the domain, exclude from the domain. So if I set 2 minus x equal to 0, well, if I go ahead and subtract 2 from both sides, I'm going to get negative x is equal to negative 2, and this would basically imply that x equals 2. So this is a value for which the denominator would equal 0. So its domain, we're going to write the domain here, would be this negative infinity up to 2 in union with 2 to infinity. Okay, so this would be the domain of that function there because we had to exclude that x value. Cheers.